Hi everyone, my name is Sajad. Today I'm going to talk about our joint work with my supervisor Ruth, who is also here in the audience, called Refining the Sample Complexity of Comparative Learning. Okay. So when we talk about the performance of machine learning models, usually the first thing that comes to our mind is their accuracy or their loss value. However, nowadays, especially that we are deploying these models in real-world applications, we might also want our models to satisfy some other conditions. For example, we might want our model to be fair so that it doesn't give advantage to a certain group of the population. We want our model to be interpretable so that we can explain why it's behaving in a certain way. We may also want our model to be fast. For example, if we ask ChatGPT a question, we want it to answer it right away. And we also may want our model to be small so that we can, for example, deploy it on our edge devices. So one way that this is done in practice is to train a huge model that can achieve high accuracy, and then use that model to train a smaller model that satisfies our requirements. So, however, current theoretical frameworks such as realizable or agnostic model don't really satisfy this, don't really capture this scenario. So that's why here we want to introduce a new pack type framework that can model this. So the framework, we call it proper comparative learning, which is a modification of general comparative learning, which was introduced by Hu and Peel in 2023. So we have the usual suspects. We have X, our domain. We have the label space Y. Here, this is a classification task. We work with partial hypothesis classes, so we also allow our hypothesis to have a star in it, which we can think of as abstaining to predict a label. So in comparative learning, instead of just having one hypothesis, we have two hypothesis classes. One of them is called the source class, which plays the role of the more complex teacher model, which we assume that generates the true labeling of the data. Then we have the benchmark class, which has the nice properties we want it to have, and we compare our learning with. So more formally, proper comparative learning is defined like this, which is the simple proper learning with some modification, which is the simple pack learning with some modifications. So first, we assume that the distribution D is realizable by the source class. Second, we compare our learner with the best in the benchmark class. And finally, we force our learner to output a hypothesis from the benchmark class. So now, perhaps the most natural proper learner is the ERM. And we want to define a dimension that can capture the sample complexity of ERM. So this dimension is we call it a one-sided neutral graph dimension, which is similar to the graph dimension, with the distinction that here we kind of assume the base function in the graph dimension is in the source class. So more formally, we say a set U is shattered, is a one-sided graph shattered by S and B if there exists a source function S such that it's defined on U, and for any subset V of U, there exists a benchmark function that is equal to S on V and differs from S on the rest of U. So we define the graph, one-sided graph shatter dimension to be the size of the largest set that is shattered by the pair. And one thing to emphasize is that this can be really different from the graph dimension of the source class or benchmark class, and it could be finite even if they are infinite. So our first result is that the sample complexity of ERM benchmark ERMs is characterized by this graph dimension. Our second result is that this lower bound is actually tight in the sense that there are classes such that this lower bound holds for any proper learner, not just the ERMs. And finally, we get that in this setting, actually proper learnability is different from learnability, meaning that there are classes that are learnable but not proper learnable, which is the interesting part here is that those classes can be total and binary, which is not the case in the usual pack setting where this separation happens for infinite label spaces or partial classes. Now, as this setup is somewhat between the realizable setting and the agnostic setting, so we might wonder what is the exact rate of over epsilon. Is it the fast rate of 1 over epsilon or the slow rate of 1 over epsilon squared or something between? So we show that there is a dimension that actually can control this exact rate, which we call mutual star dimension, which is inspired by a dimension called hollow star dimension, which was introduced by Steve and Nikita and their colleagues. So a mutual star of size k, I'll explain it on the figure here. So we have a source function that is not realizable by the benchmark class, but if you change every label in a point, it is. So for example here, this labeling 1, 2, 3, 4 that comes from the source class is not realizable by the benchmark class. But if we change the label of 1 to 6, for example, it is realizable by the benchmark class. So this must hold for any direction. So this is like the first direction, second direction here, it changed the label from 2 to 5, here 3 to 5, or here like from 4 to a star even. And the mutual star dimension is defined as the smallest size of a mutual star. Now we show how we can get slow rates. So the theorem is that if the mutual star dimension is finite, we get a rate of 1 over epsilon squared inevitably. So the way the proof works is that, well, consider a star that is defined on a set of size k, and consider the set of distributions that are almost uniform on this set, but one of them has a mass of epsilon less than the others. So now if we want to have a successful proper learner, it should find that point with the smaller mass, which requires 1 over epsilon squared number of samples. If you're familiar with the coin flipping problem, it is similar to that when k is 2. Now, we get a full picture for the proper case of, for the binary case. So we saw that if this mutual star dimension is finite, we get a lower rate, lower bound, a slow rate lower bound. But if the mutual star dimension is infinite, but the VC dimension of the source is also infinite, then proper learnability is impossible. However, if the mutual star dimension is infinite, but the VC dimension of the source is finite, then we actually get a fast rate of d over epsilon. Well, the additional requirement is that the domain x is countable. So one might wonder what happens if x is actually uncountable. So following the second talk by Julian, there are cases where the proper learnability is undecidable. And here, unexpectedly, this undecidability is for total binary classes, whereas in the usual pack learning, this only happens for multi-class with infinite labels. How much time? 2.5 minutes. So our main focus was the proper case, But we also wondered whether we have this fast versus the slow rates in the general comparative learning where we don't have this requirement on the learner. So the result of the previous work by Hugh and Peel, they showed that the general comparative learning is controlled by something they call mutual VC dimension. And however, as you can see, there is a gap in terms of the dependence on epsilon, where their lower bound is 1 over epsilon, but their upper bound is 1 over epsilon squared. So here we define some dimensions that we show control this rate, although we have some open problems. So the first one is the diameter of hypothesis class. So the diameter, you can think of it as the maximum Hamming distance between two hypotheses in the class. So, but here we have partial hypothesis classes, so you can we restrict the domain to be in the support of one of those hypotheses. The other one is the diameter prime. So here, instead of restricting the domain to the support of only one of these hypotheses, we restrict it to the joint support, so the intersection of the two hypotheses. And finally, we get something, we define what we call VC diameter, which is something that captures both the complexity of the source class and the benchmark class. So it is the supremum cardinality of a set that is shattered, VC shattered by the source class, and also the diameter of benchmark on that set equals the cardinality of that set. Okay. So this is our result. So we first show that if the VC diameter dimension is infinite, then a lower bound of 1 over epsilon squared is inevitable. Next, we show that if either of these dimensions are finite, we get a fast rate of the over epsilon. So, for example, if VC of the source class is finite, you can just realizably learn that source class, and which would imply learnability of, which would imply comparative learnability. And the diameter is also similar, but I'm going to skip the proof of that here. So just to summarize our contributions, we introduced the, yes, but just one thing that I should mention here is that this lower bound and upper bound are not matching, so this is an open problem. We would be happy if you could solve it. So to summarize our contributions, we introduced the proper comparative learning setup, and we showed that there is a separation between proper learnability and the general learnability. Then we also defined this new dimension, mutual one-sided graph dimension, and show that it controls the benchmark ERM learnability. We also give a full picture for the binary case, for binary proper comparative learning. And finally, we identify some general conditions for when we can get linear versus quadratic rates in terms of 1 over epsilon for both the general and proper comparative learning. That's it. Thank you.
Okay, thanks. Any questions? We have time for one or two. Okay, well, I have a question. So if I'm understanding correctly, in the proper binary case, there's actually like a dichotomy in rates where you either have epsilon squared or epsilon. So do you expect in the, so if this is correct, or is there?
Or you are not learnable at
all. Or not learnable, sorry. Epsilon squared, or like infinite. Right, in the learnable. So this seems really interesting. Do you think that this is also, there's this dichotomy in these other open cases, like in the general case, or do you expect there's intermediate epsilon?
Yeah. So that's actually what we wonder. I mean, it could be that we have intermediate results, but we actually don't know yet fully. But the special cases that we have, or like in previous works that they work on, I don't know if you're familiar, what's called as a deterministic agnostic learning, there's only fast and the slow rates. There's nothing in between them.
Right, but I guess there are these works where if you like condition on what opt is, right? Steve and I think others have
Yeah,
these,
yeah.
that then you can actually interpolate between epsilon and epsilon squared.
So that's one possible thing to say, but we are not sure about.
Thanks. Any other? Yeah. Oh, yeah. Back there.
So how do you characterize the learners? Like, do you give a construction-based learner? And if you give a construction-based learner, how do you construct the learner?
So do you mean for proper learn?
Yeah, for proper or improper, where you have this.
Yeah, so yeah, we do define actually, we have a construction of the learner for the proper case.
I see.
Yeah,
And for
so,
the improper case?
for the improper case, also we have an algorithm for that.
Like,
Yeah.
is it based on OIG or like, how do you construct the improper learner?
So for the improper learner, so for the like for example, when the VC dimension of the source is finite, our learner is just any realizable learning algorithm for learning the source class.
Okay.
Or like for example, when the diameter is finite, then we can like we have a special algorithm, but it is based on previous work. So I think it will need like it will take some time, so we can.
Got it. Okay.
talk
Thank you.
about it.
Thanks a lot.
Great. Let's take any other questions offline, and let's thank the speakers, all the speakers, one more time.